So, we're going to get started. And like I said, every topic here really has textbooks, and we have to obviously get done in couple of classes. And I'm sure you didn't hear one bit that there were textbooks for the Markov-Decision processes and reinforcement learning. You are happy enough to get out of the topic. Probably you won't feel as much for this neural network stuff because presumably that's what we do the course for anyways. But we still will basically do about 2 classes, today's and next class. And then we will come back to the notion of learning in other times, other types, other places in the class. We'll probably do decision tree learning when we do propositional logic, and we'll definitely do statistical learning when we do Bayes networks. Okay, so this is just, in some sense, learning without it. That's what neural networks unfortunately is. It works. We have no actual clue, and we don't really know how to prove that it's doing anything right. And in fact, most of the theory for neural network-based learning comes from statistical learning, which you will get to translate. Okay, so hopefully it will sort of get done in 3 different pieces. Okay, so before I get started, so today's class, as I said, based on the class preference, today's class will be ending at 11:20. It should off at 10:55. That's exactly 25 minutes more, and we'll do it for 2 more classes, and that will basically take care of the 1 class I missed. Okay, so today as well as Wednesday we'll do that, and so essentially you've got longer classes for neural networks, so it's kind of better than so other thing, of course, is that we are in fact going to have like a review session for the midterm in class on Monday, on next Monday, and then the exam itself will be in class on next Wednesday. Okay, and I sent you a specimen exam with solutions and explanations of solutions, so you get a sense of how an exam might look like. But that's basically what I have regarding administrative stuff. Are there any other questions before we get started? Okay, so just remember that last class we were looking at, we got into learning from the reinforcement learning side, and we basically wanted to set up a way of approximating the function underlying the values of the individual states. And so you assume that each state is written in terms of some features, and the value is a function of these features. Now, what kind of a function? We started with the simplest possible function, which is a linear function, which is W1 times F1 plus W2 times F2 plus W3 times F3, and then all you're supposed to find out then the learning part is finding out what the function is. And since we have decided the functional form, because the form is the linear function, learning part would then be figuring out what should be the weights of this linear stuff. Okay, I want to start from there and essentially connect it to basically general supervised learning and neural networks. So just to remind you, what we did then is imagine you were given up front, act as if you were given as if like a set of states and their values. Okay, and so these are basically called the training data in essence. Okay, you have the values. Now each of these states are written in terms of their feature values. Each state has features f1, f2, fn, and then presumably you're writing the value of the function of a state as some linear sum of the feature values, linear weighted sum of the feature values. And as I said, the thetas are really the weights. So you can actually think of them as W1, so this should be either 0 by the way, W0, W1, W2, etc. And then you're just trying to find those weights. The word weights is what you would use in in the neural networks typically, but essentially that's what we are going to do, right? So the question, of course, is there are obviously an infinite number of these kinds of functions, right? For any given state, you know the f1, f2, f3, etc. up to fn, presumably. Okay. Once you know that, how to combine them, of course, you have to pick some vector w0 all the way up to wn. Okay. There are infinite number of such vectors. Those are called the weight vectors. Okay. So the question is, what's the best weight vector of them all? That's what you're trying to find out. And to figure that out, what we did was we will try to actually see what is it that we're trying to do. A good function, hopefully, in this particular case at least, essentially tries to minimize the predicted value of the state, predicted value, function value of the state. We had theta minus what you know is the actual value for that state. Okay, that's the difference. You predicted something, actually the real value is something else. There's a difference. Somehow the difference is your kind of a loss. You know, if you could basically make that difference zero, then your prediction is kind of good. Now, of course, keep that all this in the background with the fact that making the prediction value to be zero on just training data is essentially compression. And that there was this whole entire discussion about how learning is more than compression. You know, that you just don't want to get the error zero. But however, the best you really can do is take this error and try to, so and then basically we had Sj, we had theta of Sj minus V of Sj. That is the difference, and I just squared it and took a half, and I told you that half is just so that 2 gets cancelled out. But the square essentially ensures that if you underestimate or overestimate, both of them are considered errors, right? And so that's why you don't want them to cancel out. And then we also talked about the fact that we could have actually added up the absolute values of the error. But as it turns out, absolute values as a function is a bad function. It doesn't behave well. It basically is not differentiable. Okay? And so because it's not differentiable, because essentially an absolute value function, in case the mod x looks like this. This is absolute value of x. Okay, so at this point, if you're coming from this direction, the slope is this. If you're coming from this direction, the slope is this. So continuity is a necessary but not a sufficient condition for differentiation, differentiability. This is stuff that you know from calculus. So we don't actually use the mod x, instead we use x squared because x squared looks kind of like that. Okay, and that's nicely well behaved function. Okay. And so then we're trying to minimize this. This is what we said we'll do. And to minimize this, we essentially realize that the way to do this is, of course, you take the derivative and equate it to zero. If you can solve the partial derivative, equate it to zero, and you can get a closed form solution, you are done. In your entire life, you pretty much will get a closed form solution sometime much later. For example, in Bayes networks, it turns out you can get closed form solution. Okay, but most of the time, and also when you did line fitting, for example, in general, you have a bunch of points on the xy axis, and you're trying to find what's the best line to fit. By the way, that line fitting is what we are doing here right now, in essence. Okay, it turns out line fitting also actually had a closed form solution, but closed form solution sometimes may or may not occur, but always you can do the gradient descent, which is keep taking small steps towards in the direction opposite from the gradient, because the gradient basically will tell you the direction in which the function is increasing locally. And so you take a small step in the opposite direction, the function is reducing locally. Not globally, but locally. Okay? And then, so to do that, what we did, and then basically, if I happen to know the gradient vector, then essentially the theta vector would be taken, the current theta vector would be updated by current theta vector minus alpha times the gradient vector. Notice these two vectors will have the same size, because the vector is actually there are as many dimensions as the number of features. And that's exactly what you will have from the partial derivatives too. There are just as many partial derivatives as there are weights. Okay, so you should be able to subtract one vector from the other. So if you then look at it from the point of view of the individual dimensions of the vector, then what you're doing is for each individual dimension theta I, you're taking its old value theta I minus alpha times just that particular partial derivative with respect to theta. Right? Okay? This alpha is called the learning rate. If it is basically too big, then you're assuming local is equal to global and you're making big jumps. If it's too small, you realize that the direction is only correct locally and that it might change very quickly, and so you will make very small steps. Okay? And if you make it too small a step, then you will take forever to reach the minimum, whichever is the closest minimum. If you take too big a step, then you just jump across the minimum, go somewhere else. Okay, and so you kind of, this is first of the fudge factors. These are, for quantum of difference, these are called, learning rate is called a hyperparameter. So parameters are figures, these are the weights that you want to learn, and then there's some more parameters, some more fudge factors that we have to figure out. Okay, that's like learning rate. And the learning rate is anything else other than the weights are called hyperparameters. Okay, and so basically for now we'll just assume that we set hyperparameter value of alpha to be some number, let's say 0.2 or something. And then of course, then you just have to do this particular partial derivative at that particular point. Notice that you think of derivatives as obviously closed form expressions, but they have actual numeric values. If you introduce the value of the x, y at that point, you will get the actual partial derivative value. It will be a number. Okay, again, for some people this may be hard to visualize, but most of you should be able to realize that derivative is ultimately a number, okay, at any given point. Okay, it's a real number. So then you essentially did the dou Ej by dou theta I, that would be written as dou Ej by dou v theta and dou v theta by dou theta I. And that helps because essentially v theta is written, so basically this is the way v theta is written. So dou Ej by dou v theta Sj is essentially taking this whole thing and this whole thing and differentiating it with respect to v hat theta. Okay, and so that would just get 2 times this whole value, 2 times this value, because x squared is 2x. And then that half and half got cancelled out. So you just have v theta minus v Sj. Times I need to actually do the chain rule part, which is dou v theta by dou theta I. Now, this part obviously depends on how v theta is defined in terms of thetas. In this particular case, it turned out that it was defined as a linear function. Okay, imagine you define v hat theta in a very different way. In fact, one of the other things that people tend to differentiate is e power minus sigma fi theta I fi. Okay, I could have written it that way. That would be the function that I'm using to actually predict. Okay, and so instead of, and if I do that, then I have to, this derivative here will be the derivative of this function. We are lucky because here the derivative is the derivative of the linear function. Okay, and then so basically it turns out that it is in fact, if you differentiate this expression with respect to theta I, the only thing that is actually a variable is the part theta I fi si. Everything else is constant. And then you differentiate with respect to theta I, you get just fi si. Right? What is fi si? That's just the feature value of the ith feature at that particular state. Okay, so what you are saying is that theta I, the ith weight, should be changed in the following way: alpha times the difference between the overall predicted value of the state and the overall true value of the state, times the feature value for that particular weight, so fi, for that state. You see what I'm saying? So it's like you make a step. In general, one of the things you can do is actually, if you're trying to go, if you're in a particular, if you're in a, like a hill and you want to go to the top of it, then you can just make small steps that increase your height. That's enough. Okay, the real question is, what direction is the best direction? And so the partial derivative is telling you the direction, which is the best direction. The partial derivative in this particular case is actually really proportional to the difference between predicted and true value and the actual value of the feature for that state, the height feature of that state. Okay, so that's what you basically got, and then if you just make this change, repeatedly, okay, then you will get all the theta weight values will essentially come to a local mean. That's the basic idea. So, in the temporal difference learning for linear approximators, this is again, I'm just repeating what I said last class because I'm just going to go from there to subtrams, is essentially just like the normal temporal difference learning loop, right? Except when you got the updated value, basically, so remember the temporal difference says you should change your value to be closer to your successor's value. So according to the temporal difference, your true value is this updated value for now. And the current theta function is probably predicting a particular value to this state. So the difference between those is the error. Do you see what I'm saying? And you are essentially shifting weights a little bit to reduce that error. Not to make it zero, a little bit to reduce the error. Okay? So that's basically what you're doing here. Okay? And notice that, in fact, even though we started by acting as if we had all the states and their values up front, in reality, what we are doing here is sort of an online learning. It's a sort of an online learning because you would only get each particular state, during the temporal difference, each particular state's value is updated. And so that gives an error, and that error signal is used to update the weights. Now, when you update the weights so that you would be correct with respect to this state, you are in essence changing everybody else's values. This is the part that I was going on and on towards the end of last class, that when you change a specific state's actual value, you don't change anybody else's value. Whereas if you change its value by changing the weights that are used to combine the features, you're changing everybody's value. A little bit. That's why you should be careful, you don't make big jumps. Okay? Anyway, so that's about TD for linear approximation, and you can do the same sort of a thing for Q-learning. It turns out, essentially, it's more or less the similar idea. Again, you will have the updates in terms of individual weight vectors, individual weights in the vector would be updated a little bit based on the Q update. Remember, the original TD and Q learning essentially will tell you how much to change the current Q value or the current value of a state. They themselves are asking you to change a little bit. I don't know if people realize now that there are like two learning rates that we're talking about. There was a learning rate which tells you to become closer to your neighbor's value function. And there is another learning rate which tells you to actually how to modify the weights. So it's like a double online stuff that's going on here. That's what is online update of Q learning, online update of TD learning. Okay, and I believe one of the parts in the reinforcement learning project will actually get you to do that. And when you do that is when you realize, the Pacman actually gets really quite. Okay, so this much we kind of decided. We talked about last class. Now I want you to, even though we came into this basically trying to do reinforcement learning more efficiently, in essence what we did is we acted as if, basically our function was this, right? This was your function, yes, okay? And so I can imagine this in essence as some sort of a unit where this is f0, f1, etc., fn. These are theta 0, theta 1, etc., theta n. This guy sums theta I, fi. Okay? That's what you did, in essence. And if you did this, you can think of, this as a little unit which has getting inputs. The inputs are connected to the unit by weights, and it's multiplying the weights by the inputs and outputting stuff. This, by the way, is called a linear perceptron unit. It's like one of the simplest units. It just takes the weighted sum of its inputs. Linear perceptron unit. One thing that you can do is actually, after you do this, you can then take, rather than just send this out, you send some g of, some g function, some threshold function, what we call threshold function of theta I fi. So these g functions, typically the threshold functions might look like that. So if the weighted sum is below this direction, you just output 0. If it's above this direction, you output 1. That's a threshold function. This is actually called the step function. Now, obviously, step functions are the best threshold functions, but they are pretty bad from the calculus point of view, because step functions cannot be differentiated. It turns out there is another nicer function called 1 by 1 plus e power minus x. How does 1 by 1 plus e power minus x work? Whenever you're thinking of a function, consider very large values, very small values. Right? So when x is minus infinity, a very large negative number, this will be a very large positive exponent. 1 by 1 plus e power, let's say 10,000. By the way, you remember that e is a number, right? Okay. E power 10,000 is a huge big number. 1 by a huge big number, close to 0. So at x on the negative side, it will be sort of like that. Actually, on the negative side, it will be like this. And when x becomes very large positive number, let's say plus 10,000, this will be e power minus 10,000. That will be close to 0. So 1 by 1 plus 0 is 1. So it will be like this. In this region, however, it slowly turns. This is called the sigmoid function. Okay, and you can use this sigmoid function instead of just a threshold function. Now, as to why do we even care about using this additional g function, it turns out that we came to perceptrons from the point of view of compressing, essentially easily remembering the value function using just linear sums. Okay, but it turns out that if you want to essentially make, now that you came to this, you can make an analogy to some extent to these quote-unquote neural networks, the neurons in the brain, the biological analogy. Okay, and there is enough reasonable support to say that the neurons in the brain have some properties such as they have some inputs. They're essentially, the neurons are connected to other neurons through synapses. Okay, and so essentially they are multiplying their inputs by some weights. They're summing them, and typically you understand that most of the neurons tend to have gating behavior. So there is like a gating function, G, and then out comes a output of that. Right now we are thinking only in terms of single unit, but the expectation, the reason you actually are paying attention, to the extent you're paying attention, is that you want to be able to combine the output, let's say, of this unit as the input of somebody else's, some other unit. And if you do that, you get a stacked neural network. At that point, if you can somehow figure out how to combine, learn these weights in the same way, then you have a way of learning the neural network. Now, here is the question. The reason G, imagine G is just a linear function. If G is a linear function, and then I basically stack a whole bunch of perceptrons, that's such that some perceptrons outputs are going to other perceptrons as inputs, and then so on. If you do this, then essentially the input to output relation is going to be some big function of the inputs. What would the type of that function be if G is always linear? It will still be linear. Okay, so if you use G as a threshold function, as a linear function, then putting huge number of perceptrons will still get you only a linear function. Of the many functions in the universe, linear functions there are infinite number of linear functions, but that infinity is much smaller than the bigger infinity of all functions. I don't know if that made any sense. Right? So if you want, actually, if your input, if in the particular data you have, the input is some arbitrary nonlinear function. Nonlinear only means it's not just linear. Okay, nonlinear function of the inputs. Then if you are using perceptrons with a linear threshold, it will never work. We eventually have to use some nonlinearity. The moment you put some nonlinearity, then you are guaranteed. It turns out, one of the beautiful things which I said last class, that in fact, if you just have 3 layers of perceptrons, if you just have 2 layers of perceptrons, that is, inputs are connected to some inputs you are connected to one perceptron and the outputs of them are connected to another perceptron. If you just do this, and if you are allowing any number of perceptrons in this layer, and if they are nonlinear threshold functions, then there is a theorem that says that for any arbitrary function, there exists some configuration here that will essentially approximate that function to epsilon accuracy, for whatever epsilon you take. So you went from linear to suddenly I can take any functions. Questions? Okay. Okay. So before going forward, I want to differentiate. So the funny thing we are doing right now is we are talking about supervised learning, which is a huge entire field. But we made our way into it in this funny way. We went through reinforcement learning into supervised learning. And the most obvious thing to do in the context of reinforcement learning is essentially approximating the value function. And the value function happens to be essentially a real quantity, a real number quantity. So in essence, you are approximating a function whose outputs are real numbers. Okay? If you are trying to learn a function whose outputs are real numbers, then that particular learning problem is called regression. A fancy name. Okay? In many cases, actually, imagine instead of learning the value function in the reinforcement learning, you decided somehow to learn the policy. Okay, so the idea would be for each state there will be feature values. Okay, and based on the feature values, rather than go from feature values to the value number, I want to go from feature values to what action should I do. Now imagine this was a sort of a, the grid example, where you can go up, go down, go left, go right. So this function now only has 4 outputs. Irrespective of the state, the policy can only tell you to do one of the 4 actions. Do you guys see this? It's a function, all right, except the domain is essentially real numbers of these features, and the range is a discrete set. The range is a discrete set. It corresponds to either go up, go left, go right, go down. If you are learning those kinds of functions, you call that a classification problem. I'm confused as to how people are so, is it complete understanding of everything going on, or you've given up on that? Right. So basically, you keep hearing about regression versus classification. Supervised learning can do both regression and classification. I would almost talk as both of them together in this case. Up until now, we looked at regression as a specific example, linear regression as a specific example. And in fact, one of the things that people do to do classification is you could actually do logistic regression. What logistic regression is that what logistic regression does, what logistic regression does is it essentially puts the summed up Fi values, Wi Fi values at 1 by 1 plus e power sum of theta I Fi. And you know that logistic regression will give you discrete values approximately, even though it's a continuous function. So in fact, one of the funny things about classification tasks in general that you should be worried about is classification makes the function have discrete output values. Why should you be worried about it? Yes? Differentiation. You guys understand that? Okay? If you have functions that have discrete output values, that means it's going jagged, up and down like this. There will be basically whatever is the value, the output value of the function is either 0, 1, or like one of 4 different values. In the case of the grid example, is go up, go down, go left, go right. Do you see what I'm saying? And discrete functions, you can't do gradient descent. So you convert it into a continuous function. It looks kind of steppy, but it is actually locally continuous. There is a lot of interest in looking for functions like sigmoid because, in fact, one other function, it turns out, which looks like sigmoid is tan h. Another function which looks like sigmoid is tan h, and that looks like that. Like that. Tan h function. Again, this is stuff that you know from long back, from your trigonometry classes. Tan h is hyperbolic tangent. Okay? And the hyperbolic tangent also has this nice steppy shape globally, but locally it is continuous. So the way you will wind up doing classification is to do classification at all, you do wind up needing this G function. You realize this now.